Hello, everyone, and welcome to Particles in a Box, episode number 5. Today, we are going to be discussing two-dimensional motion. So sorry for the couple months off. I had some personal stuff I needed to deal with, but we are now back, and we're talking about two-dimensional motion. Why just stick to one? So we're going to be going from the one dimension, which we mainly focused on our kinematics episode, which was episode number 2. So if you want to check that out, I'll leave a spot for that. But in that episode, we drove the kinematic equations as though they could work in 3 dimensions. So we use like vector notation, and so now we're going to be going from 1 dimension to 2 dimensions. So first of all, a little bit of review. When we drove those kinematic equations, we said that the acceleration was constant for all time. So there was no difference in acceleration over time. It was always a constant value. One of the equations that we drove was this one right here. The displacement is equal to 1/2 times the acceleration times the time squared plus the initial velocity times the time. That equation is going to be used a lot in today's episode. But then we also drove a couple of other equations. We drove another one for displacement that doesn't depend on acceleration. It just depends on your initial and final velocity. And then we drove another equation for the final velocity in terms of the initial velocity, the acceleration, and the displacement. So with that being said, let's get into the thick of things today. So today, we're going to be talking about two-dimensional motion. Or more specifically, we're going to be talking about a very specific case of two-dimensional motion, and that is called projectile motion. Okay. So what projectile motion involves is that it is a set of constraints. It's an idealistic situation where we just take where we take some assumptions and we say that they're true, and that allows us to study this more in depth and discover some properties about it. So number one, we are assuming that we are near the surface of the Earth. Okay. The reason why this matters is that the acceleration due to gravity, the constant g, in order to apply our kinematic equations, the acceleration needs to be constant. And so if we say that we're near the surface of the Earth, it allows us to keep this value of g as a constant. When we do gravity farther down the road, the acceleration due to gravity will not necessarily be constant. And that will change how we describe the motion that's going on. Number 2 is that we're going to assume there's no air resistance, okay? In 2 or 3 episodes, the plan is to do air resistance, but in this episode, we're going to ignore air resistance as that, again, makes our acceleration constant g variable, okay? And it changes how that acceleration works. One thing that we're also going to be using is that as a result of these 2 constraints, we know that the change in the y position is equal to this expression. So we got 1/2 times the acceleration due to gravity g times the time squared plus the initial velocity in the y direction times the time. Okay. So we'll be launching things at some angle and at some velocity, vi. Okay. And we care about the vertical component of that here. So that's what we care about. And then for our change in x position, it's just v naught xt, okay? As I'm going to say numerous times in this episode, there is no acceleration in the x direction. I'm going to say that again. There is no acceleration in the x direction. I'm going to say that for a 3rd time. There is no acceleration in the x direction, okay? Do you get it now? There's no acceleration in the x direction. Okay, good. Okay. So with these constraints and with these equations, we can describe a specific case of motion that is a pretty good approximation of what actually happens and is a good place to introduce motion in multiple dimensions, especially for people who are new to physics or just getting into physics. So first off, we have a couple of graphs here. And so we'll start over here on the left, okay? This is a graph of the y position with respect to time, okay? And what we have here is we have our acceleration, we have our initial velocity, we have d, which is our initial displacement, which is going to be 0 in this case. We have theta, so the initial angle at which we launch our particle, right? there's some angle to that, and then we have our final time and our initial time. Okay, just so I can help scale this graph. So when you're taking a look at this, right, it's an arc. This is parabolic. It is a quadratic equation. If you look up here, right, we have our nice expression. Okay. This v sine theta comes from the fact that we, since this is a graph of y here, right, this side length y over here for our velocity, v sub y, so v sub y is equal to, or v naught sub y, this is the initial y velocity, is equal to vi sine of theta, okay, because we care about the y component. So as you can see from this graph here, right, it's just a nice arc. We start at 0, we launch, and we go, and then eventually we hit the ground at some point over here, okay? The rest of the stuff down here we ignore because we're not going through the ground or anything like that, okay? I also noticed that the velocity is just a linear line. It just consistently goes down because we have a constant acceleration down here at the bottom. But the other thing that you need to notice is that there's a value of the velocity where it is 0, right there, okay? And that's going to correspond to the maximum height of our projectile, okay? So when we launch something, the velocity is eventually going to hit 0, and then that's going to correspond to the maximum height. Now, if we go over here to the right, this is just the x position. So that's x with respect to time, okay? So our horizontal position, you'll notice that we have a cosine theta because the initial velocity in the x direction is vi cosine of theta. And so since there's no acceleration, the value of the acceleration is always 0. The velocity is constant, and the x position just goes up linearly over time. So what I'm going to do here is I'm going to take our plot here. We'll plug it in, just so I can show you a little more about what's going on here and show you some different cases and how this can change if your parameters change. First thing we're going to do is we're going to put our velocity to positive, and then we'll set our initial displacement to 0, and we'll launch at some angle, and this way we can get everything in one graph here, right? So, as we change our angle, right, the ball hits the ground sooner, right? And then as we increase our angle, it takes longer for the ball to hit the ground. So you can change the angle, right? It just changes how quickly we hit the ground, right? You can change the initial velocity. If you lower the velocity, again, the quicker it's going to hit the ground. You can also change the acceleration, which just like opens up the parabola a little bit, right? And then if we set our acceleration to positive, right, it goes upwards instead of downwards. So it's like it's flying almost. And so you can just kind of move the sliders around and see how the graph changes. So over here, right, if on the last slide we were doing the x and y position with respect to time, but now this is a graph of y with respect to x, okay? So this is how you would actually see the projectile flying, right? In the previous slide, that was a time graph, so it's not actually how you would see something flying, right? Like it would not, like right here, right, given these constraints, the ball would not actually hit the ground at, what is this, like 1.4 meters or whatever. It would actually hit the ground at 10 meters, okay, which is, quite a big difference. And so, yeah, so you just have like different constraints, right? And you get to see different, it's still a parabolic shape, right? That doesn't change. So we'll blow these up here so that we can see what's going to happen. So our acceleration is still -10. We'll set our velocity to positive, and then we can change our angle. And so you can see here now that, right? So now as my angle increases, right, the ball is actually going less far. As I continually increase my angle, the ball goes less and less far. And as I hit 90 degrees, it's going to be 0, right? And then as the angle flattens out, it gets longer, longer, longer. But then eventually it's going to start moving back. So like here, right, we kind of, like right there, we kind of hit like right here, we sort of hit a maximum at about 10, right? And then it's going to start shrinking closer and closer and closer back to 0. So this suggests that there is some sort of angle that we can maximize the distance that the ball is going to travel when we launch it, right? Since if the angle is really small or if the angle is really large, we don't go that far. But if we're somewhere in the middle, there's an angle where we can maximize the distance that we travel. And so that's something that we're going to be exploring as we go here. So first thing we want to explore is the maximum height. So if we go back over here, right, I mentioned that over here, right, the velocity becomes 0 in the y direction. And so because of that, there's a critical point, and that means that there's a maximum value there. And so we want to find out when does that maximum value occur, and where does that maximum value occur? So it turns out that the where, or the value of the maximum height, is a lot easier than the when. The when is going to vary depending on constraints, but which we'll get to here in a second. So first of all, we know that's going to occur at some point x comma y, where the velocity in the y direction is equal to 0. Okay, that's where our critical point is at. We know our expression for y from earlier, and we also know our expression for x from earlier, and we can also get the velocities as well. Okay, the velocity in the x direction is never going to change. It's just the same as the initial velocity in the x direction, but the velocity in the y direction is going to change because we have a gt. Okay. But what is this g, right? If you're not familiar, g is equal to negative 9.8 meters per second squared. Okay, that is the acceleration due to gravity near the Earth's surface. That is the value that we use for these problems. It can get more complicated than that, but this is the value that we're going to be using for all of our problems. So we're going to try to find the maximum height of a projectile using these equations. So we set it equal to 0, and we're going to find the time at which this occurs. So it turns out that the time at which we reach the maximum height is negative times the initial velocity times the sine of the initial angle over the acceleration due to gravity. So what we can do is we can take that, we can plug it into our y equation, and we can get some interesting looking stuff. But when we simplify it down, we end up getting this expression right here. And so again, some people are like, oh, negative sign, right? Does that mean that it's a negative height? That doesn't really make sense. Again, right, our g is negative. So if you take out the negatives, they'll cancel out, so you get a positive answer. Right, if you had a positive acceleration, well, instead of being a maximum height, it would be a minimum height. So that would be kind of weird. But we do have maximum height, right? If g is less than 0, which it is for our problems, you will get a positive value, and it's the initial velocity squared times the sine squared theta of our initial angle over 2g. So then, okay, we found the maximum height, but what's the maximum distance that we're going to go? What's the maximum in the x direction that the projectile or ball or whatever you're launching can go? So it turns out that there's two different ways that you can actually do this. The first way is that we can use our result from the previous problem, the time that it takes to get to the maximum height. And since this is quadratic, it is symmetric. The motion is symmetric, so we can use that property to say that 2 times the time it takes to get to the maximum height is the total time that the ball is going to be in the air. Okay. This is only true if the maximum distance is given from flat ground. So you you launch your ball and you end up back at the same y position at which you started. Okay, so none of the like, oh, we're going like this or we're doing something like this, right? The y values need to, the initial and final y values need to be the same in order for this to be true. Okay, and so we are assuming that to be true for this case. So we got 2 times the time it takes to get to our maximum height is the total time that our ball is in the air. And so when we plug that in this time into our x equation, right, we get this expression right here. Some of you who are more experienced, maybe have a little more mathematical background, you might recognize that 2 sine of theta times the cosine of theta is equal to the sine of 2 theta. Okay. And so that's how we get over to this expression right here, where we get rid of that coefficient of 2 and the cosine goes away and we get a sine of 2 theta. I personally like this form a little bit better, especially when I'm teaching people who are a little bit who are new to physics or are at the more introductory level, because if you were to ask somebody, okay, what do you think that this might depend on, or what do you think our final answer should look like? They're more likely to say like, hey, right, there should be a cosine involved, right? You know, if you look at this at face value, right, it's like 2 theta. How do we end up with a 2 theta, right? Like, where does that come from, right? That's a lot harder to explain to somebody, right? But telling them where the cosine comes from, it's like, oh, it's part of the horizontal component of the initial velocity. It's like, oh, okay, that makes a little more sense, right? Both forms are equivalent. It just, I like one form personally a little better than the other. But there's another way to do this. So say, for example, you didn't know that the motion was symmetric, right? You can instead, we know that our y positions are, the change in y position is 0, okay, right? The initial y position and the final y position need to be the same. And so we're going to solve for the time, and since we have a time squared, this is a quadratic, so we're going to use the quadratic formula. We don't have any plus c, so that's 0, so that's pretty nice. That makes it a lot easier on ourselves. And so what we end up getting is we get that the time can either be 0 or it can be -2 times the initial velocity times the sine of theta over g, which is hey, pretty similar to this over here, right? So that's good. That means we're doing something right. We ignore the 0, right? Because 0 would mean that we, just end up back over here, right? Like we never moved anywhere. We didn't move. So we're assuming that we did move, right? And this would be a minimum, right? 0 would be a minimum, not a maximum, and we want a maximum. So then you can plug this time back into the x equation, and voila, you get the same answer once you cancel out the negative with the negative from the g. Okay. So that is how we find the maximum distance that a projectile can go, assuming that we are on that we're launching this where the initial y and the final y are the same. If they're not necessarily the same, you have to do a little bit more work. And when we do problems, we'll do an example where we need to do a little more work. So we're gonna throw up a bait warning here, right? So like I've mentioned many times, is that the initial and final positions of x and y will not always be 0, right? In a lot of these derivations, I assume that x and y initial were 0, right? That may not necessarily always be the case. Most, like 90% of the time, if you set up your problem correctly, you can make it so that your initial x and your initial y are 0, but there might be situations where that's not necessarily true. And so that's why it's important for me to throw this up here, in that they might try to throw a situation at you on an exam or a homework problem where those aren't necessarily true. And I want you to be prepared and recognize, hey, you still have to go through the steps to make sure that, hey, can my equations that I'm using apply in this situation, right? As that is important. So, so we have a couple of so we got an equation here for the range. Are there some properties of this equation that are interesting? And it turns out there are. So if you remember, so if we go back a couple of slides here, right? When I was manipulating this, right? So I increased the angle and the distance started going down. And then as I decreased the angle, at some point, the distance also started going down, right? There was some value for the angle where the distance was maximized, right? And so we're going to try to find that. What is the angle that we want to launch our projectile at so we can get the maximum distance on it? And it turns out that it is at this theta is equal to pi over 4. Okay. So one way that you can kind of do this is intuitively is, okay, if I plug, is that I want this to be at a maximum, right? I know that my VI and G are constant, right? They're not going to change. I'm only changing my angle right now. And so when is sine of 2 theta at a maximum? When is sine of 2 theta equal to 1? When is this true? And it turns out that's when theta is equal to pi over 4, right? 2 times pi over 4 is pi over 2. Sine of pi over 2 is 1, okay? So that checks out there. But is there maybe another way to where we can show that there's a maximum pi over 4 and then maybe discover another interesting property, right? And it turns out that there is. So we're going to make our delta x a function of theta, okay? We're holding the initial velocity constant. We're holding g constant, right? We're not going to be changing those. And so what we're going to do is that we're going to make x, we're going to do pi over 4 plus delta. So we're going from pi over 4 and we're adding some additional amount of angle, okay? Some additional amount. But we're going to say that delta is, has to be less than pi over 4. And it has to be between 0 and pi over 4. Just so that we're not getting into some weird situations in other quadrants on our xy plane. So one side we're going to have pi over 4 plus delta, and the other side we're going to have pi over 4 minus delta, okay? We want to see if these are equal, okay? Because if they are equal, what that means is that for a given delta, if you add that delta to pi over 4, and you subtract that delta to pi over 4, you're going to launch a projectile the same distance, okay? So that means if you launch something at 70 degrees, right, and you launch something at, what would that be? Well, maybe let's use the example of, we launch something at 65 degrees, or we launch something at 35 degrees. Wait, did I do the math right on that? No, 55 degrees and 35. So say we launch something at 55 degrees and something at 35 degrees, right? So that would be a delta of 10, right? Those objects would actually go the same distance. And we want to see if that's true or not. So we're just going to plug our value pi over 4 plus delta into our equation, and then our pi over 4 minus delta into the equation. And we end up getting pi over 2 plus 2 delta and a pi over 2 and minus 2 delta. And we have to use an additive trigonomic identity. So cosine of pi over 2 is 0. So these terms go to 0. And then the sine of pi over 2 is 1. Okay? So it leaves us with a cosine of 2 delta is equal to the cosine of negative 2 delta. So because cosine is an even function, where the cosine of phi is equal to the cosine of negative phi, these are indeed equal. This checks out. So this means that these two expressions are equal. Okay? That is crazy. So if you launch something at 55 degrees and 35 degrees, the delta x is the same. Okay? If you launch something at 70 degrees, right, and you launch something at 10 degrees. Oh wait, would it be 10 degrees? Why I'm trying to do math on the fly here. Yeah. Wait. There's no way. Why is my math completely breaking down here? If it goes to 70 degrees, that's plus 5, 50, plus 25 degrees. You want to subtract 25 degrees. Yeah, wait, that would be 10 degrees. What? Wait, that doesn't seem right. But yeah, so if you do that, right, if you do something at 90 degrees and you do something at 0 degrees, those are going to go the same distance. If you do something at 80 degrees and you do something at 10 degrees, right, those are going to go the same distance. If you do something at 20, yeah, so it's 70 and 20 degrees. Those things are going to go the same distance, right? So that's quite interesting, right? And yeah, you know, that's interesting. So that being said, let's do some examples. So what I've decided to do is I've decided to break up the problems in the examples. Examples are more of the like introductory type problems, the ones that on the surface are probably more simple. And then in the problems supplemental episode, we'll do the big juicy like multi-step, longer explanation type problems that tend to be a little bit more mathematical. The examples tend to be a little bit more conceptual. So first problem, we have a long jumper at an angle of 70 degrees with a velocity of 7 meters per second. What is the maximum distance and maximum height of the long jumper? So we have our equations for the maximum range and the maximum height, and we know our velocity is 7, and we know our angle, and so you can just plug them straight into the formula, pull out your calculator, and you can get an answer for both of these. So the information is just given you in the problem. Just gotta plug them in, and you will get yourself an answer. Next question. One student throws a ball horizontally off of a roof. Another student drops the ball from the roof at the same time. Which of the following statements is true? 1. The balls hit the ground with the same velocity. 2. The balls hit the ground at the same time. 3. The vertical component of the velocities is the same for every moment in time. So, why don't we let's do blue. Oops. Let's do blue for the ball that's thrown horizontally. And we can do red for the ball that is dropped, okay? So drawing a picture is always helpful here. So the blue ball is going to look something like this. That's somewhat going to be its trajectory, assuming that this is an XY plot, okay? And then the red ball is just going to drop straight down, okay? There's no horizontal component there, okay? So, let's see, what do we want to explore first here? So 2, the balls hit the ground at the same time. Is this true or false? Well, we know that the expression for the for x here, right, is v naught xt, right? And we know that the expression for y is going to be negative, whoops, that's not going to look great, negative 1/2 gt squared plus a v naught yt, okay? And then for our red ball, the x position is equal to 0, and our y position is also a negative 1/2 gt squared plus a v naught yt. Okay. And so it turns out, since this ball here for the blue one is thrown horizontally, right? And then the red ball is just dropped. It turns out that both of these parts go to 0. Okay. So we're just left with the negative 1/2 gt squared part. Okay. So what this means is that the position of y for both of these is the same, okay? At any moment in time, the y position of both of these balls is the exact same, okay? And so because of that, because the y position is the same for every moment in time, you can take the derivative or just write down the expression for the velocity in the y direction. So v sub y here would be equal to negative gt. And then down here, the expression for the velocity is also negative gt, okay? And so these are the exact same expression. The times are the same because you're releasing them at the same time. So number 3 is true. the vertical component of the velocities is the same for every moment in time. Okay? What this also means is that the balls are also going to hit the ground at the same time. Okay? We are going to hit y, because these expressions are the exact same, the y position is going to be the same for every moment in time, so they're going to hit y equals 0 at the exact same time. So that is also true. But what about number 1? The balls hit the ground with the same velocity. Okay. So we showed that the y velocity when they hit the ground is going to be the same because it's the same for every moment in time. But what about the x velocity? Well, the x velocity for a red is always 0, but for the blue, there is some component of the x velocity because we threw it horizontally, right? So there's going to be some component in the x direction. So this is not true. Since there's no acceleration in the x direction, we have no chance of ever getting back to 0 x velocity. So the velocity are not going to be the same when they hit the ground. So the answer for this one is going to be 2 and 3. So next question. Pretend a ball is thrown on the moon where the gravity is 6 times smaller than on Earth. Compare the values of the maximum height and the maximum range to those on Earth. So, what that is saying is that 6g sub m is equal to g of e. Okay, so it takes 6 times the acceleration due to gravity on the moon is equal to the acceleration of gravity on the Earth. Okay. And so the way, so you can, some of you might just be able to kind of conceptually think about this and be like, oh, okay, I can get an answer, right? But let's try to do it mathematically and kind of show how you can do something like this, right? So we know that r sub e is equal to 2vi squared. I'm gonna write sine of 2 theta here, just save myself a little bit of space. All over g sub e. Okay. So that would be the range on Earth, okay? But we want the range on the moon, right? So one way in which you can do this is that you can get rid of that, and you can put in 6g sub m down here, right? And so, and then what you can do is you can multiply the 6 over here. So then you're going to get 6re is equal to 2, oops, that is not very good, 2. Re is equal to 2vi squared sine of 2 theta all over g sub m. And if you think about this for a little bit, right? Okay, we have a g down here. This is now back to this form. We don't have this extra 6 over here. You will recognize that that whole part is equal to the range r sub m. Okay? So what that means here, right, is that we have 6re is equal to r of m. Okay? So what that means is that the range on the moon is 6 times larger than it is on Earth. It is 6 times larger. Okay, interesting. And that's because you have to multiply the range of Earth times 6 to get the range of the moon. So the moon range is 6 times larger. And it turns out that it is also the case for the maximum height. You can use the same sort of process, right? You know what g is, you plug it in, right? You'll recognize that, hey, this whole thing is that you'll get something with the range on the moon, and you'll get like 6h sub e is equal to an h sub m. So both of them, the maximum height is going to be 6 times greater, and the maximum range is going to be 6 times greater. Okay, so next question. If you know the position of a particle at time t and at time t plus c, can you find the average velocity between time t and t plus c, to the instantaneous velocity at all times between t and t plus c, 3, the position at all times between t and t plus c, 4, the average acceleration, 5, the instantaneous acceleration at all times between t and t plus c? So this is a little bit more of a review question. It has a little bit more to do with kinematics than our actual two-dimensional motion, but nevertheless, I think this is a good problem. So at some time t, we have our particle up here, and then at some time t plus c, we have our particle right here. Okay, so let's just go through each item one at a time and see if we can figure out if these are true or false. So 1, the average velocity between time t and t plus c. So if you remember from the kinematics episode, the average velocity is just equal to the displacement over the change in time. Okay, and so we know what the change in displacement is. We know what the change in time is. So bam, you can totally find the average velocity given the information that we know. The instantaneous velocity at all times between t and t plus c. Well, if you remember, the instantaneous velocity is the tangent line to the path at any particular time. So the problem here is that we don't know what this path between this is going to look like, right? It could be a straight line. It could be an arc. It could be a different type of arc. It could be some squiggly, random, loop-de-loop thing, okay? Although what I drew there wasn't a function, but if you do something like this, well, that, like some sine cosine thing, that's also a function. So each of those paths that I drew has a different instantaneous velocity at each point along that path, and we have no clue about the instantaneous velocity. We have no idea what that is. 3, the position at all times between t and t plus c. Well, again, right, like you could have an arc, you could have a line, you could have a squiggly line. We know nothing about the position between these two times. We just know that at time t and at time t plus c, the particles are at those two spots, but in between there, we have no idea. So we have no idea what's going on there. The average acceleration. So for the average acceleration, right, you need to know the change in the average, or you need to know the change in the velocity average over the change in time. And the problem is that we have no idea what the velocity is at this time, right? We don't know the instantaneous velocity. We don't know. It's like it could be. So it's either average or instantaneous, but we don't know anything about the velocity at this moment. It could be at rest. It could be moving. Like I don't know, right? Like we don't know. So you cannot actually find the average acceleration because you do not know anything about the velocity at those particular points. And number 5 is also not true. You can't find the instantaneous acceleration. Again, we don't know anything about the path. We don't know anything about the instantaneous velocity, so then we don't know anything about the instantaneous acceleration. That just isn't going to happen. So the answer for this one is just 1. Okay, so what we were so at all given points along the ball's trajectory. So this is just a fairly average parabola, right? Nothing super special. It's just a typical path that a ball would take in its trajectory in projectile motion. And so we just want to rank the magnitudes of a bunch of different things: the x and y position components, the total distance component, the components of the velocity and the total velocity, and then the acceleration components and the total acceleration. So we'll start out with the acceleration in the x direction. If you go back, you remember that I told you something. There is no acceleration in the x direction. That is always 0. So all of these are equal to each other. Okay. Now a sub y, we're using kinematic equations for this. The acceleration is constant. It's not 0 like in x. It's negative 9.8. But again, all of these are equal. Okay. And so what does that mean for our total acceleration? It's just since all these were equal in all their stuff, the total acceleration is always equal, and it's always negative 9.8 in the y direction. Okay, so it's always pointed downwards at 9.8. So yeah, so that's our answer for the acceleration. How about the velocities, right? How do the velocities change? Well, x, right, like I said, there's no acceleration in the x direction. The velocity in the x direction, therefore, is always going to be constant. So it's never going to change. So for all of these, it is equal. Okay? And then for v sub y, though, because we do have an acceleration, right, it's going to change. Okay, so it's no longer constant, right? That's going to change. So at position 1, right, we just launched, right, we're going to have our greatest magnitude upwards. At 2, it's going to be a little bit less. At 3, it's going to be 0. We have no vertical component because that's our maximum height. And then at 4, we're downwards. And then at 5, we're downwards with the same amount as 1. Okay? And so this is where you got to be careful when you're reading the problem, right? It says magnitude. So what's the magnitude of the vector? Okay? And so, well, it's downwards, and you would write negative amount j hat or negative amount y hat, right? The magnitude is the same, right? Because the magnitude of a vector, right, is the, what do I want to use? Is the y component squared plus the x component squared, and you take the square root of that, right? So because you square the negative number, and then you take the square root of that, you get a positive number for the magnitude. If it said the value, right, then they wouldn't necessarily be the same, okay? But because of that, we know that 5 is equal to 1, which is greater than 2, which is equal to 4, which is equal to 4, which is greater than 3, okay? So there's that. And then we want the total velocity, which is going to mirror what we had for v sub y. Again, the velocity in the x direction is always the same. So it's just going to mirror whatever happened in y. So now we're going to do our positions, okay? Well, x, well, okay, if we put our axes up here, right, we're going to assume that let's maybe actually just use a nice little line thing here to make those straight. So if you do x, right, you can see that, okay, so 5 is the greatest, and then 4, and then 3, and then 2, and then 1, right? So there you go. 5 is the greatest, 1 is the least. For y, right, it's a little bit different, right? 3 is our biggest one, and then 4 is going to be equal to 2, right? Which is greater than 1, which is equal to 5, okay? And so then for d, right, you know, you kind of have to match these things up. So, well, yes, well, 5 is the least there, right? It's the greatest over here. So 5 does actually have the greatest amount of displacement in this case. And then 4, and then 3, and then 2, and then 1. That might not be intuitive immediately, right? But our max range is greater than our maximum height. So that is true, is that 5 is going to be the greatest distance away from the start, and then 4, and then 3, and then 2, and then 1. Okay? So, if we go to the next slide, this is just a summary of what we just did. But before we go, and before we leave this problem today, there's something that I wanted to bring up about this, and that I drew some arbitrary curve here, right? And I wanted to ask you, what if our curve looks something like this, right? And we had 3 up here, we had 2 over here, we had 4 over here, we had 1 down here, we had 5 over here, right? How would this change our answers, right? Where the maximum height h is greater than our displacement d, okay? So h is greater than d, right? But here, right, d was greater than h, okay? Well, it turns out our acceleration is still the same, right? The accelerations don't change, right? The velocity rankings also don't change either. So that doesn't matter. Our x rankings don't change either, right? 5 is still the greatest, right? Our y rankings don't change either, right? 3 is still the greatest, and then 2 and 4, and then 1 and 5, right? However, our d does change, right? Because the distance here is now greater than our distance here. So 5 can no longer be the largest, right? So then the question becomes, okay, well, is it 3? Is it 4? Is it maybe neither? Right? So in our supplemental episode, this is going to be one of the questions. If you have the max height larger than your range, what is true about the ranking of your total displacement? When is the ball actually the farthest away from you, right? So if you're up for a challenge, you can think about this and maybe try to come up with an answer. I challenge you to do so. But that is going to be a question that we are going to explore in the next episode. One other thing before we go, though, is I want to go back to this here, right? Where I said if you have the same delta, right, and you go up a little bit in angle and you go down a little bit in angle, and those differences are the same, right? You're going to go the same distance, right? The range is going to be the same. Some people get this a little bit mixed up. The range is the same, but the time it takes to get there is not the same, right? So if I launch something like this, right, and I launch something like this, right, the time for the one that's going higher is going to be greater than the one that was zinged low, right? They end up in the same place, but the time to get there is not necessarily the same. And so that's a misconception that I want to make sure that I bring up before the end of this episode, and that's why there's a reason why you might want to choose one of these over the other, even though they're going the same distance, is that one might take longer or less time to get there. Okay. So do keep that in mind. That's why it's often better to shoot something low and have it get there rather than lobbing something, because you are more likely, because it'll get there sooner if you shoot it low. And you know, the longer the time the projectile is in the air, if you're trying to hit like a ship or something like that, right? Well, the ship's going to have more time to move around and try to avoid that projectile, right? If it's just lobbed over there than it is if it's just quickly shot pretty close to the ground. So that is going to be it for this episode. I hope you enjoyed. I hope you learned something new. As always, please like, comment, and subscribe. If you feel free to send me an email if you think I made a mistake or you have a question or you want some further clarification. Please feel free to email me. And so until next time, have a great day, and I will see you in the next episode.